Hello appraisers, this is Brandon with Spark for Appraisers, and I'm making this video about regression. I know you've had enough regression videos from me, and believe me, I think I've made enough to last me a while. But I heard some appraisers saying some things recently, and I just wanted to make a clarification video about a couple different topics. One is the difference between sample and population, the other being about standard deviation. So first, what you see in front of you here are two different formulas for what is essentially the same thing, standard deviation. So when you calculate ordinary least squares regression, which is the most common type of regression that appraisers probably use, it's the one that's like built into Excel. When they calculate that, they need to calculate standard deviation in order to fully calculate out the regression analysis. And so I have the standard deviation formulas up here, also because we're going to be talking about standard deviation later. But the reason I want to talk about it is because some appraisers may believe that regression is not very reliable or maybe not even worth utilizing at all, because typically when statisticians use regression, they're using it on a sample of data. And you can make an argument, and I would, that when appraisers are running regression on a set of data, it's not actually a sample. A lot of times, or most of the time, it's probably the entire population. For example, if someone says, go find all the properties competing with your subject property, you go out and you do a search and you come back with 40 over the past year or 2 years or whatever. You come back with 40 sales of properties that are competing with your subject property. Some people might say that's a sample because obviously it's not all the properties, but I would argue that that is the entire population, because that is the entire population of competing properties, assuming you did your search well in the MLS or whatever you're using. So I would argue that that's the population. We're not trying to extrapolate information about that sample of data to the entire population. We're basically taking that data, analyzing it on the entire population to understand, in theory, what like an adjustment might be. So that's the difference between sample and a population. Think of it as like the presidential election. You know, when election comes around and you have all these companies saying, oh, there's a 60% likelihood that X is going to win the election. But that's all based on a sample of data. They don't know how every person is going to vote that's actually going to vote. They just poll certain people. They take a survey and they poll X number of people and they extrapolate that to the entire population. But that's not, as appraisers, what we're typically doing. We're basically just running data on the population, on all our competing properties, or all the single family homes in the defined neighborhood boundaries, or whatever it is. That's typically going to be a population. And so just because it's a population does not mean that it's not worth running regression analysis on that data. This video is not an argument that regression is the end all be all. I'm not saying that it's even super great. I'm just saying it's another tool to use. It's another method that you can use to help you form an opinion on what the adjustment might be for whatever it is you're analyzing. And so just because it's population doesn't mean that you shouldn't use whatever regression it is that you want to run. One other thing I want to bring up regarding sample and population is you can see these formulas are virtually identical. This one is, and by the way, this is just a Google search. So I just did a Google search for formula for the sample standard deviation and a formula for the population standard deviation. And you can see that they're virtually identical. The only difference is, Greek letters versus non-Greek letters. And we have down here, you divide not by the total number of observations, or for an appraiser, maybe the total number of sales. You divide by the total number of sales minus 1 when you're doing the sample, and that's known as the degrees of freedom. Over here on the right, when we are calculating standard deviation, we use the Greek letter sigma, and we divide by the total number of sales, not the total number minus 1. And you can see there is a couple other differences, but really, like X bar, that's the average of all of the observations. And mu, the Greek letter mu here, is the same thing, but it's for the population, not the sample. So anyways, this whole I equals 1 and n here, that should be here as well. It's just not, but it's the same thing. Those are the same. Really, the main difference is dividing by n minus 1 versus n. Anyways, just wanted to point that out. It is a little bit different. In our adjustment tool, we are assuming a population. So just so you know, that's how it works. Also, in our tool, we will provide a ton of documentation, so you could go and replicate the results if you wanted to. And in that, we describe, it's a long document. It talks about all the different types of regression, paired sales, sensitivity, all that stuff. But it does provide, when we're talking about ordinary least squares regression, where we utilize these formulas, it shows that, and you can see we are using the population formula, which is using the Greek letter sigma. And the same thing with the other formulas, you can see that. Okay, anyway, so just that's out of the way. Now, I want to talk to you briefly, hopefully briefly, about standard deviation. So I have a video about R squared and the correlation coefficient and why I don't believe that it's super important that, and sometimes even might possibly lead you to get inaccurate results if you rely on R squared. Now, that was that video. This video is basically arguing the same thing, but about standard deviation. So let's bring up a spreadsheet I made ahead of time. I realize it's a little ugly, but essentially we've got a chart here. This chart is just plotting out all these data points, and what we've got is basically 5 properties. This is a totally made up scenario, but 5 properties that sold on January 1st every year from 2015 through 2019. So for 5 years, sold January 1st, and each year the sale price went up by $15,000. So we got 5 properties. They each sold on January 1st, 2015 at slightly different prices, but each one of those went up by exactly $15,000 every subsequent year for 5 years, and that's what this is. So we run a quick little ordinary least squares regression on this data. This shows that values are increasing at $41.06 per day. The R squared is 0.5294, and the standard deviation is 29,155. Now, just for clarity's sake here, when the regression is telling us that things are going up at $41.06 per day, multiply that by 365 days in a year, and you got your $15,000. So this regression analysis is very accurately telling us exactly how much things are going up, which is $15,000 a year or $41.06 a day. So that's great. The regression analysis is working. Now, this R squared is not great. It's not a really high R squared. A lot of people that would scare them off from using it. But again, I would argue, don't let that scare you. Just because it's not a great R squared, this adjustment result that we're getting from this regression analysis is actually super accurate to the actual increase in market conditions over this period of time. Now what we're going to do is I'm going to strip out 3 of these sales. Now look what we have. That's this right here. You can see it's in a slightly smaller font. This is showing you just those 2 sales. And down here, standard deviation, I have it showing you in a slightly smaller font there. The standard deviation went up and the R squared went down. Now, just as a refresher, lower R squared is typically worse and higher standard deviation is typically considered worse. The standard deviation went up, which is not a good thing, and the R squared went down, which is not a good thing. So a lot of people might think, okay, well, these are not reliable results because the R squared went down, it's actually pretty low, and the standard deviation went up. So if I were to look at these 2 analyses side by side, I didn't know anything else, then I might say, yeah, let's lean on this analysis, not this one, because of this data. My argument here is it doesn't matter. Not to argue that you should never look at R squared or you should never look at standard deviation, but just that maybe you really shouldn't place a lot of weight on that, but more place the weight on your experience as an appraiser in the market. You know when you get ridiculous adjustments from regression analysis and you just disregard them. You don't even consider them, regardless of what the R squared is and regardless of what the standard deviation is. Now, this is an example where actually our regression analysis, as far as the appraiser is concerned, which we're talking about making adjustments, the result here is 41 bucks a day or 15,000 a year, and the result here, $41 a day or $15,000 a year. So our adjustment result is identical. It knows that things are going up at $15,000 per year, despite the R squared being worse and the standard deviation being worse. Again, higher standard deviation, not as good. Lower R squared, not as good. My whole point here is that it's not making a difference. Like, this result is just as reliable as this result, despite that. And then, so one last thing I want to mention on that is just imagine this scenario, and this is a very possible and probably likely scenario when it comes to regression analysis. Full bath, let's say for these same properties that are right around the 100 $250,000 to $300,000 price range. Let's say one regression analysis gives us $6,000, the other gives us $80,000. And let's say their R squared is 0.5294 and 0.3333 and 36,742 and 29,155. So the R squareds and standard deviations are identical to the analysis over here that we did on sale prices, but this is on bathrooms. And one analysis tells us that the bathroom adjustment, full bath adjustment, is $6,000, and the other tells us it's $80,000. Now, based on this information, this having a higher R squared and a lower standard deviation, your gut might be that, oh, well, this is the better number to use because we've got a higher R squared than this, and we've got a lower standard deviation than this, and both of those are better. It's very likely that you could have something like this where you actually have a far worse adjustment even though the R squared is better and the standard deviation is better. So what I'm saying is rely on your expertise in the market. You most likely have years and years of experience or decades of experience. You know that 80 grand, I'm assuming that's the case for if this was your market of $200,000 homes, 80 grand is not an adjustment to use for a full bath in a $200,000 house. But $6,000 is probably a lot closer to the adjustment you would actually make for a full bath. Again, that doesn't mean this is the number you should adjust for. It's just more likely that this is an accurate number than this one. So I would probably throw this away and say that's just not useful to me. 80 grand is a ridiculous number that I would never make, and I might use something closer to 6 grand. Now, I'd probably want to run some other methods, like maybe a paired sales analysis or a sensitivity analysis or depreciated cost, which is great to run on for a bathroom. So run those and see if you get numbers similar to this. But this could very well be a good starting point versus this, which we can just throw away because you know as an appraiser that that is not a good number to use and you can trash it despite it having a better R squared and a better standard deviation. And I'm using better in quotes here, by the way. Anyways, I think that's it. That's all I wanted to say. Sorry for the long video again on regression. Hopefully it was helpful to you overall. Let me know if you have any questions, and thanks for watching.